Welcome to physics. Today we're starting our new unit on momentum. And if you missed class today, you missed a pretty fun day. This is a picture of an egg hitting the wall. And that's right, we got to throw some eggs around the classroom today. Now, we didn't throw any at the wall because we kind of already know what's going to happen, right? If you throw an egg in a wall, it's going to break. But what we did do is we threw an egg at a sheet. So since you weren't here, I've included a video, and we're going to watch Mr. Higdon and see what happens when he throws an egg at a sheet. So let's start this. And don't worry about large impulse and large stop time. We're gonna talk about those. But here's Mr. Higdon. He threw a strike there. Pretty good form. And as you can see, our egg is just fine. Didn't break at all. Let's check it out in slow motion. Got the good hip turn there. He's got a good whip in his arm. So I'd say this is a nice pitch right here. You might have seen how the sheet moved quite a bit, okay? So our goal for today is to understand enough physics to explain why the egg broke if we were to throw it against a wall, but why it didn't break when we threw it against the sheet. And you're probably already hopefully coming up with some ideas. So a lot of times what I hear is, well, the sheet is very soft, which it is, but soft isn't really a very good physics explanation. And sometimes people say, well, the sheet has a lot of give. And I agree, it absolutely does. But I think we can do better with our physics explanation. So we're going to go ahead and take some notes, and then we're going to come back to this video, and we're going to see if we can explain it in detail as to why the egg didn't break. To do that, we have to go back to Newton's second law. So you remember Newton's second law from first semester, and it said F net equals ma. So let me get my pencil set up here. There we go. We would write F net equals ma. And remember, m just stands for mass, F net is the net force, and a stands for acceleration. So we accept this as a given. We trust Professor Newton. We know he knows what he was talking about. And you also remember the definition for acceleration. Remember, acceleration was defined as a change in velocity over a change in time. So what I'm going to do is I'm going to rewrite Newton's second law and change up the variables a little bit. So I'm going to go ahead and I'm going to plug in for acceleration. Instead of writing a, I'm going to write change in velocity over change in time, which I can do. And then I'm going to go ahead and bring that delta t over to the other side. And I'm going to see that the equation looks like F net times delta t is equal to mass times a change in velocity. Now, for the purposes of this this part of the year and this unit, we tend to drop the net part. So I'm just going to write that as just F times delta t is equal to mass. And change in velocity, we can do better than that. We can write that a little bit differently. So recall that a change in anything, including velocity, is just the final value of that thing minus the initial value. And earlier in the year, and we talked about how, hey, your change in money for the day, if you work, right, your change in value for the day, your money for the day is the final value that you have when you go to bed versus the initial value that you had when you woke up. So if you made $100 that day, your change in money was plus 100. If instead you didn't work that day and all you did was spend money, maybe you went to the mall and bought something for $100, your change in money would be negative $100. So we always take the final value minus the initial value. So in that case, and I distribute that m, I'm going to find that F times change in time is going to be m times v final minus m times v initial. And this is going to be kind of our formulation of Newton's second law for this part of the unit. Now, we're going to go ahead and we're going to do a couple things with this. First, we're going to give this a special name. This is called impulse. Okay, and I'm going to use capital I to stand for impulse. Impulse is going to equal to a force times a change in time. We've defined that. I could have called it anything. I could have called it Fred. But physicists decided that when you multiply force times delta t, delta time, change in time, we're going to call that impulse. Let's take a look at our units for impulse. Our units for impulse are going to be the units of force, which are simply newtons, times our unit for time, which is simply a second. So our units for impulse are just going to be newtons times seconds. And if we want to give, this is kind of the equation that defines impulse. We could write this out in words, and we could say that impulse on an object, okay, when we impart or exert an impulse on an object, is applying a force for a given time period. Okay. So if we have a large impulse, that means that we either, okay, so that means that we either have a large force applied over a large time interval, or both, right? I could have a large force over a small time. I could have a large time interval but a small force, or I could have both, and that would result in a large impulse. So that's the first thing that we're going to go ahead and define from our rewritten formulation of Newton's second law. The next thing we're going to define is based on this right here, okay? So we're going to define that as momentum. So we're going to use lowercase p, and it does have to be a lowercase p, is equal to momentum. Why do we use p? Because m is used for everything else. It's used for mass, it's used for meter. I think it has something in chemistry like mole or molarity. Too many m's. So we decided to go with p is going to stand for momentum. And momentum is going to equal mass times velocity. So remember, mass we're going to measure in kilograms, and velocity we measure in meters per second. So our units for momentum are going to be kilogram meters per second. You could also write this, it's the same thing as writing kilograms times meters all over seconds. It's exactly the same thing. Now, you might notice something here, and you might say, well, wait a minute. This looks kind of weird because if we have that impulse is equal to a change in momentum, because that's really what we have here. So I could look at this equation and I could say impulse is equal to a change in, and we're going to get there. Impulse is equal to a change in momentum. But let's check out these units for a second. So we have that impulse is newtons times seconds, and we have that momentum is kilogram times meters per second. And if we have this equality up here, the units have to be the same on both the left and the right side. They don't look like they're the same, but they actually are. Because remember, a newton is really just a kilogram meter per second squared. So if I replace this newton with kilogram meter per second squared, and I multiply by a second, and I ask, well, is that really equal to a kilogram times a meter per second? I see that this s cancels with this squared, and indeed those are equal. So when we're talking about momentum, I can go ahead and I can use either newtons times seconds or kilogram meter per second. It doesn't matter because they're going to be equal. Now, let's go back to this equation that we saw earlier real quick. And we said that we had that force times change in time is equal to mass times v final minus mass times v initial. Whoops, I'm going to go ahead. I use an O there. I want to use an I. Now, what we can do with this is we can write that this right here is equal to I. So I'm going to write I equals, that's impulse. This right here is the final momentum because that's the final velocity. This right here is the initial momentum. So I get that impulse is equal to the final momentum minus the initial momentum, but that is just the change in momentum. So if I know the change in momentum, I know the impulse and vice versa. This is going to help us explain what happened with the egg that we threw into the sheet. So we're going to look at a bunch of different variables, and we're going to compare the egg that hit the wall to the egg that hit the sheet. And we're going to say, well, is the one that hit the wall greater, less than, or equal to? So for instance, let's consider mass. Okay, let's consider mass. Is the mass of the egg greater when it hits the wall, less when it hits the wall, or the same? We're going to assume that the egg had equal mass, whether it hit the wall or it hit the sheet. So we're going to assume that those are equal. Now let's talk about the initial velocity, because we have to consider all of these variables here. We got to consider the initial velocity, the mass, the final velocity, the time, and the force to figure out why one broke and why one didn't. And hopefully you see that whichever egg experiences the bigger force is going to break. Right? That kind of makes sense, right? If you had an egg on the table and you were trying to crack it open, you would apply a force to it, right? You would hit it with something. And if you hit it really lightly, it wouldn't break. But if you hit it really hard, it's going to crush. So whichever of these two eggs experiences the greater force is the one that's going to break. So we've got to get to this, because I know a lot of information about these things. I don't know what's happening with the force yet. So when we look at the mass of the eggs, we're going to assume they're equal. When we look at the velocity that we could throw each egg with, let's assume we threw each with the same velocity. It was about, let's say Mr. Higdon, he's got a really constant throw, and he throws each with the same velocity. That means then that the initial momentum for each egg must have been the same. Why? Because initial momentum is just mass times initial velocity. So if the masses were equal and the initial velocities were equal, their initial momentums must be equal as well. Well, now let's consider the final velocity. What is the final velocity that each one reaches? Well, eventually each one comes to rest. They each reach a final velocity of 0. So in this case, each of their final velocities are the same, and they are in fact 0. So that tells us that their final momentum also has to be equal. Well, if the final momentum is the same for each egg, and the initial momentum is the same for each egg, that means that the change in momentum for each egg was the same as well. They each had exactly the same change in momentum. Well, if that's the case, given this equation right here, and they each have the same change in momentum, they must also experience the same impulse. So each egg experiences the same impulse. Here's where it gets interesting. Let's talk about the time it took for each egg to stop. Imagine an egg hitting a wall. That egg stops almost instantly. So the time it takes to stop is very small. Then consider the egg that hit the sheet. The sheet stretched back, moved forward, the egg rolled around a little bit, and finally it came to a stop. So the time it takes for the egg to stop that hits the sheet is significantly greater than the time it takes the egg to stop that hits the wall. So the time for the hit the wall is much less than the time to hit the sheet. Now we can see what happens to the force. If the change in momentum for each egg is the same, but one egg experiences a really long time of impact, that egg that experiences the really long time of impact must experience a really small force. So the egg that hit the sheet has a very small force compared to the egg that hit the wall. So the egg that hit the wall, right, has a much bigger force. That's why it broke. That's not easy to come up with, but that's the physics explanation as to why the egg that hits the wall breaks. It's because the change in momentum for each of those two eggs is the same. Therefore, each egg experiences the same impulse. And if the impulse has to be the same, but one experiences a small time, the one that experiences the small time has to experience the bigger force. So we can write that out, because this is your notes, and we want to make sure we're clear. And we want to say the impulse and delta P are the exact same. So the impulse and change in momentum are the exact same whether the egg hits the wall or the sheet. I realize I probably have a little more room on my page than yours. Sorry about that. Okay. The egg breaks when it hits the wall because the wall causes the ball to stop in a small amount of time. Because the wall causes the egg to stop in a small amount of time. Thus increasing the force. The sheet allows the egg to stop over a long period of time. Thus decreasing the force to a point where the force is not large enough to break the egg. We call this type of a demo an equal momentum change or an equal impulse demo. So I would call this an equal impulse demo. We have a few more of those listed for you on Schoology. We're going to talk about a couple different types of scenarios. The first one, just like the egg and the sheet, are those equal impulse demos. It's an equal impulse, it's an equal change in momentum. We can also look at situations where there's a large momentum change, right? And with a large momentum change, right, we're going to have a large force for a long time. You might just have a large force for a shorter time or a long time for a smaller force. But normally, if you want to maximize the change in momentum, you want to maximize the impulse, you're going to want a large force for a long time. That's why if you play a sport, you might have heard a coach say something like, hey, follow through. If you're a batter, if you play tennis, if you play golf, at some point you may have heard a coach say follow through. And the reason the coach is telling you that is because you want to have a very big change in momentum. If you're hitting the ball, you're kicking the ball, you want a large change in momentum. So you want to apply a big force. And that's really determined by how strong you are. There's not a lot you can do. You can work out, go to the gym, right? You can get a little stronger. But your follow through is something anybody can control. So for our baseball player here, the longer time that he spent, by that way, that's Tim Anderson. He's not on the White Sox anymore. The longer time that the ball is in contact with the bat, the more the change in momentum will be, and the faster the ball will leave the bat. So we want a really large change there. We want a large change in momentum. So, because we want the ball to completely reverse directions, right? So let's say the ball's coming in at 100 miles per hour towards the batter. We want it to leave at 100 miles per hour in the opposite direction. So that's a change of 200 miles per hour. Because think about it. Remember, velocity has direction. So if the ball is coming in and we have an initial velocity of 100 miles per hour, and we want a velocity of, we'd have to call this negative 100 miles per hour. I know it goes against our convention of left to right. That means our change in velocity then is equal to negative 100 minus 100 miles per hour. That's negative 200 miles per hour, okay? So we want to completely reverse direction. So the ball leaves the bat with a maximum velocity. So when your coach is telling you to follow through, that's because they understand a little bit of physics. Well, maybe they understand a lot. Who knows? Okay. So we want a large change in momentum. We talked about that. We want a large change. So we want a large change. Here, we'll put this in a large change in velocity. That means we want a large change in momentum. Because change in momentum is equal to mass, because the mass doesn't change, times the change in velocity. So if we want a large change in velocity, we need a large change in momentum. Well, that means we need a big impulse. Oops. That means we want a large force over a long time period. I don't like the word over. People think that means divide by, and it doesn't. I'm going to put a large force for a large time period. So when the coach says follow through, they're not asking you to change how hard you're swinging, the force. They're telling you to stay in contact with the ball for as long as possible. So follow through means stay in contact, in this case with the baseball, for as long as possible. So that's a lot. That's a lot of information, and we're not even done. But let's summarize our equations a little bit, because these are really important. So the first equation that we have is that momentum is equal to mass times velocity. Notice that's not change in momentum, that's just momentum. Okay? So that's momentum. And usually we use units of kilograms, meters per second. Our second equation is that impulse is equal to force times a change in time. That's impulse. And we normally use newtons times seconds, but we can use kilogram meters per second as well. Our third equation is impulse is equal to a change in momentum. This is called our impulse change in momentum equation. And it's really important. The other equations that I like to just mention is that a change in velocity is final velocity minus initial velocity. A change in momentum is P final minus P initial. Or you could write change in momentum as mass times change in velocity. These here, okay, this equation, and this equation, you just should really know because they flow from the other equations. But these equations right here are equations that I will always give you on any quiz or a test. So if you haven't already, it's time to get out your calculator because we're going to practice some of this. So let's keep it simple to begin with. We're going to ask a simple question. What is the momentum of a 12 kilogram ball that is moving at 3 meters per second? So they're asking for momentum. So when I consider my equations, I want to find P, and I know that P is equal to mass times velocity. Now there's no initial velocity, there's no final velocity. I just know that this ball is traveling at 3 meters per second. So I can plug in what I know. I know that the mass is 12 kilograms. I know that the velocity is 3 meters per second. And you probably don't even need your calculator to tell you that that's 36 kilogram meters per second. That's it. That's all there is to that question. So pretty straightforward. Obviously, most of our questions on a quiz or a test or an assessment won't be that simple, but if you got to be able to do that one to do the rest. Okay? So that's pretty straightforward. Next question asks, what impulse does a bat impart to a ball if the bat hits the ball with a force of 243 newtons and remains in contact with the ball for 0.034 seconds? So our impulse equation tells us that impulse is equal to a change in time. We know the force, it's 243 newtons. We know the time that it takes that the force acts on the ball is 0.034 seconds. That's a delta t. We started our timer at 0 and it ended at 0.034 seconds. So here's where you want to get out your calculator and make sure that you got 8.26 Newton times seconds. So that's a pretty straightforward calculation as well. The hard part is knowing which equation to use. Well, if I'm trying to find impulse, I better use an equation with I in it, okay? The next question asks, what is the change in momentum of the ball from problem 2? So what impulse does the ball what impulse does the bat impart to the ball? Well, I know a force and I know a time, but my equation for momentum is mass times velocity. Well, nowhere in this problem do I know anything about the mass of this ball, right? Because I'm on problem 2. I don't know, it's not the same ball as problem 1. I don't know the mass and I don't know the velocity. So this equation is not going to be super useful. But looking back at your equations from the previous page, you see another equation. You see that impulse is equal to a change in momentum. Well, I know the impulse. So I already know the change in momentum because it has to be the same as the impulse. It's 8.26 Newton seconds. So the hardest part about this unit with the math anyway is understanding that you have several different equations to choose from and you have to be clever with which one you choose, okay? The last thing we're going to look at, because these notes are pretty long, the last thing we're going to look at is one more demo. So we've considered equal impulse demos. So equal impulse is when we have two different situations and each object is undergoing the same impulse. So the egg hits the wall, the egg hits the sheet. Same egg, but different situation. They're undergoing the same impulse. Then we looked at large impulse situation where you want to impart a large impulse to an object. So for instance, kicking a ball or hitting a ball. Now we're going to look at situations where we have really small, almost zero momentum change. And you've probably at some point seen the tablecloth trick. If you haven't, that's okay. I'm going to show you the tablecloth trick in a little bit, okay? But first, let's see if we can figure out what's happening here. With the tablecloth trick, what we do is we put a tablecloth on a table, and then we put a plate or a couple cups or something on there. And if we pull the tablecloth really quickly, the plate or the cup or whatever won't leave the table. It won't fall over. It won't even move. And that's exactly what we want. So in this case, we want a delta P or a change in momentum equal to 0. Well, the initial momentum is pretty simple. The initial momentum of the plate, let's say we just put a plate on there. The initial momentum of the plate is based on the initial velocity. Well, initially, the initial velocity of the plate is 0 because it's not moving. Right? The plate's just sitting there. So the initial velocity of the plate is 0. That means that the initial momentum of the plate is also 0. So what we really want, the final velocity to be 0 as well. Well, if the final velocity is 0 and the initial velocity is 0, that means that we need a change in momentum as close to 0 as possible. But if the change in momentum is 0, and we know from our impulse momentum equation that impulse is equal to a change in momentum, that means we need our impulse as close to 0 as possible as well. So if we want our impulse equal to 0, that means we need a really small force and or a really small time. Now we can't change the force much. Okay, we can't change the force much because the force between the plate and the tablecloth is a frictional force, and that's just determined by the mass. The frictional force is going to be determined basically by the mass of the plate. What we can control is we can control the amount of time that the force acts. So even though we have a friction force that won't be zero, we can get the time as close to zero as possible by pulling very quickly. If we pull slowly, it won't work. So if we pull very quickly, that means delta t is about 0, which means that the impulse is about 0, which means that the change in momentum is about 0, which means that the final velocity will be about 0. And that's what we want for a small momentum change. And that explains the tablecloth trick. So let's take a look and see what that looks like. So here's the tablecloth trick. We got a plate, we got some silverware, we got pepper and salt, we got a little cup there. And we're going to go ahead, we're going to pull on that. Okay, nothing fell down, not bad. Let's take a look at it in slow motion. There's a trick to this too, by the way. You want to pull down and out, not just, you'd never want to pull up. So if you watch the tablecloth, I'm going to pull it down and towards myself, never up. So they moved a little bit there, but not too bad. So that's the tablecloth trick. And if you go on to, oh, I don't want to stop. If you go on to Schoology, you'll see a couple of other small impulse demos. That's it for the notes for today. We'll have some more notes soon. Have a great day.